When we start to explain electrodynamics theory, there is often a rising confusion that makes listeners run away screaming. Here is an exception. This method is simple and helpful for interested people. I saw an interesting episode from the channel Veritasium explaining electrical energy flow. I like it very much because it plays with the fact that electrical energy is not flowing inside wires and that the timing is defined by the speed of light. There was a lot of reactions explaining why this should be right or wrong. It's great to have such a lively discussion thanks to Veritasium and all the reactions. However, looking at all the confusing explanations, I felt that I should explain a method to quantify this a bit. With this episode, I'm trying to mess this up completely. Of course not, don't worry. I think you will be able to follow. We will understand that it depends on the matching of the waveguide properties where and when the energy will flow in the given example. The final results will be even a bit surprising. And in addition, you will understand why these effects are playing an important role in real life and not only in funny theoretical experiments. Veritasium's example is a simple electrical circuit applying unusual long wires that make the time effect clear. We look at a circuit comprising a lamp, a battery, a switch, and the set very long wires. We are wondering after what time exactly the lamp would light up after the switch is closed. Veritasium's conclusion was that the lamp lights up after 3.3 nanoseconds, which equals 1 meter divided by the speed of light. Viewers might have expected this only after 1 second, because the length of the two wires is 150,000 kilometers, which equals half a light second. Since electricity is traveling with light speed, it would take 1 second to travel the wire forth and back. We will see that the correct answer is a bit more complicated. In this episode, we will explain when and where the energy will flow under certain conditions. There was quite a number of reactions that I have seen on my subscribed channels. There were explanations that the capacitance between the wires is the clue to understand this. Others were scribbling confusing electromagnetic fields to explain the effect. In addition, I saw computer simulations and even measurements that didn't bring it really to the point. They are all right in a sense, but not quite. Even such simple examples have secrets that are a little bit more complex. But there is still hope to understand what happens here. Engineers unmasked this a bit by developing a proper method to tackle such problems. And there is no need to apply heavy computer programs to get the answers. Let's talk about that method. In general, engineering methods are trying to concentrate on the dominant effects. This simplifies the law of nature a bit, and then we can apply the methods even to complex structures. I personally like this kind of methods because they help me to oversee a problem before I start any black box computation tool with which I feel like a monkey with a gun. One of these methods is to work with the waveguide properties of the arrangement. You might ask, hey, why should we do that? We are talking about direct current here. Yes, but this is only true in a steady state. In the moment when the switch is closed, we will see highly dynamic transients traveling along the wires. And that is why we need to look at the impedance of our waveguides as well as the reflection and the transmission factors that we possibly have in our case. The impedance of a two-wire waveguide is given by the formula ZL equals 120 times arcus cosinus hyperbolicus of the wire distance divided by the wire diameter. You can find this formula in Wikipedia. I chose the wire diameter to 1 centimeter. With that we get an impedance ZL of 636 ohms in our example. Then we assume the lamp's resistance to be 100 ohms. Together with the battery voltage we would get a nominal lamp power consumption of 1.44 watts. Now we can analyze what's going on step by step when we close the switch. You might have noticed that I'm always giving you a timestamp here in red in the right upper corner. With that trick we can analyze the problem step by step. For the next step we can simplify our problem a lot. At t equals 0 we close the switch and we look exactly at this point in time with an infinite accuracy. We have now a circuit with 3 impedances. 2 times we have the waveguide impedance plus the lamp's resistance. What will we see now? Well, we see nothing happen in this point in time because the current is just starting to flow. 3.3 nanoseconds later we can expect a current to appear that we can easily calculate applying Ohm's law. Remember, the 3.3 nanoseconds are corresponding to the 1 meter distance from the battery to the lamp, which is equal to the wire's spacing. At the moment, our arrangement is a simple voltage divider. We can simply calculate the voltage and the power appearing in the lamp at that moment. Now, looking at the magnitude of the power arriving at the lamp, we can say yes, it lights up, but not very bright. I believe with 0.0077 watts instead of 1.44 watts we can hardly see it. This is because in that moment the voltage at the lamp is pretty small, while the voltage between the wires UZL is 5.56 volts on each of the 2 branches. In case we would have a smaller impedance, say 50 ohms with coax lines, the lamp would light up at 0.36 watts, which is still only a quarter from the full brightness at this point in time. Now we let the time go further and see what happens next. Next we look at the time frame after 3.3 nanoseconds, but before half a second. As we calculated before, we have 5.56 volts entering our wire waveguides on both branches. This means that we have a transient that travels along the lines like a shock wave. With a fast oscilloscope we could actually measure it. Please note my definition of UZL indicated by the arrows. The left one goes up while the right arrow goes down. Our shockwave travels now in both of the waveguide branches towards the shortcut at the end, which it will reach after half a second. As soon as the shockwave arrives the shortcut at the end, it will be reflected and inverted. I give you the formula for the reflection factor here, which yields -1, meaning that the wave traveling back equals minus UZL. The shockwave that is coming back from the end of the wires will cancel out the voltage which was between the wires before. After 1 second it arrives at the battery and the lamp. The same applies for the wires on the other side. Let's see what happens after 1 second. Or to be completely precise, after 1 second plus 3.3 nanoseconds. You might think now that we reached a steady state here. However, this is not the case actually, because the impedance match for the wave that came back is not perfect. The shockwave that came back sees an impedance of ZL plus the lamp's resistance RL instead of ZL. This is not an ideal match. By calculating the reflection coefficient, we get R equals 0.072 and the transmission factor yields 1.072. This means that a small part of the wave is again reflected and traveling back towards the shortcut end. Then it will be reflected and inverted again and will arrive another second later, and so on. With each reflection it gets smaller and smaller. From the transmission factor we can derive that our voltage is not going exactly to 0 when it enters the wire. There is always a small voltage remaining from the echo that is coming back. Let's have a look on the behavior of our voltages in the time domain. The upper graphic shows the voltage behavior between the wires on each branch. The lower graphic shows the voltage at the lamp. That's a bit surprising, isn't it? Our lamp will light up just a little bit after 3.3 nanoseconds, and then it takes 1 second to get really bright. Then we have a step up and step down every second from the echoes. The echoes will decrease after a while, and then we reach a steady state. With our earlier calculations we have seen that the initial brightness and the echoes depend very much on the dimensioning of the lamp's resistance and the waveguide impedance of our wires. If, like in our example, the lamp's resistance is much smaller than the impedance, then the light up after 3.3 nanoseconds is very low. The bright light up happens after 1 second, and the echoes following will be relatively weak. In case the lamp's resistance is higher than the impedance, we would get a stronger light up after 3.3 nanoseconds. However, the echoes that step the brightness up and down for a while will be stronger. Let's come back to the initial questions that we had. What answers can we give now? Yes, the lamp will somehow light up after t equals 1 meter divided by c, depending on our dimensioning. In any case, higher brightness will arrive after 1 second. And then there will be echo effects that have been no options to answer. The result is a bit surprising, isn't it? It seems that all the reactions stating the original answer is right or wrong were true, however, not quite. Okay, things can be a bit more complicated than we think in the first moment. But why am I explaining all this in detail? Well, it's because these effects do not only appear in strange theoretical experiments. They are among us in our everyday life, however, we cannot see them because they are so fast. However, electrical engineers have to consider these effects in fast electronic circuits. It is a simple but powerful method because we can understand the effects appearing in fast switching circuits. Of course, we are not talking about seconds here. It is rather nanoseconds or picoseconds to be considered, because the length of practical transmission lines is in the range of millimeters to kilometers. I have to add that when we deal with real wires or transmission lines, we need to consider losses. Of course, the conductivity of real conductors is non-ideal, and a part of the energy is even radiated into space. This is why in reality we will experience attenuation and frequency dispersion of the signal along the transmission lines. As an effect of this, the signals get smoothed and decayed when they are traveling along the wires. Let's see a realistic example applying 15 meters wires where we get echoes at about 100 nanoseconds delay. In that case, the blue line here would give a realistic voltage behavior at the lamp. Let's now have a look at the Poynting vector between 0 and 1 second. Of course, it is not a single arrow. The arrow just indicates the energy flow direction in the picture. In reality, the energy flow is distributed in space according to the electric and the magnetic fields, because it is the vector product of both. Now we know that the matching of our waveguide properties of our wires and resistors are important. It has an influence on where and when the energy is flowing the moment when we close the switch. In the first moment, a part of the energy is flowing directly to the lamp, while another part is traveling between the wires. It is reflected by the short at the end of the wires and is coming back to the lamp. You could call this non-reactive power, because that portion of power is only stored temporarily between the wires. The strong transients in the first moment also have the effect that a part of the energy is radiated into space. Now you know why you can hear the clicks from your light switch in your AM radio. As soon as all the echoes decayed, the full energy flows directly to the lamp. In this steady state with ideal wires, the Poynting vector would disappear completely between the wires because there is no electrical field anymore. And the radiated part of energy is also disappearing. The Poynting vector will only remain where both the electrical field and the magnetic field are present. In the steady state, this is only between the battery and the lamp. In a realistic case with non-ideal wires, a tiny part of the Poynting vector would remain along the wires and turn even into the wires, because the magnetic field is there and the electric field is not going down to zero. This makes perfectly sense because part of the energy is consumed in the resistance of the wires. Here we are. The summary. We knew before that electrical energy is traveling with light speed in space where the electric and magnetic field is present. This is the reason why it can take the short way sometimes, depending on the waveguide properties of our arrangement. In addition to that, we learned an engineering method that allows us to quantify the energy flow in time and space with relatively easy means. The clue of this method is to work with waveguide properties like the transmission line impedance, the reflection factors, and the transmission factors. This is often a very good approximate solution to oversee a problem before you start to solve complicated field equations in time and space with sophisticated computer programs. Hope this episode was a bit enlightening and you enjoyed it. Otherwise, you can either try it a second time, or you can still run away from this kind of topics, as even many professional engineers do. However, I believe in a world of fast electronics everywhere, it has its justification. And by the way, a handy engineering value for the light speed to keep in mind is 30 centimeters per nanosecond. Occasionally there will be further extra episodes where we will cover interesting topics that are apart from the usual content of my channel. Now stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.